Okay, good day. We will now discuss, I will continue with the honors lectures, but I will recall what we did as far as the chapter on calculus of variations is concerned. You may recall that we said that in the calculus of variations, what we're doing is optimizing an integral of the following type over some region. In the case of a single independent variable x, it will be optimizing over some sort of interval. When I say optimizing, what we're doing is we're looking for a function and not a point. So find, you may recall, a function, say y equal to f of x, such that that integral is optimized, such that the integral L of, and we're keeping the function L as a function of say Ly y dashed, such that this integral is either maximal or minimal. We also showed that we can solve this problem by a problem in differential equations. We showed, let me just say that again, we showed that such a function, that is the function that optimizes, let me just highlight that optimizes this integral, the function y equal to x, that optimizes this integral, satisfies what I called an Euler-Lagrange equation. Right? We showed that y equal to f of x, that is the solution to this problem, satisfies the differential equation, and it's an ordinary differential equation, usually of second order because the function L is of first order. So it satisfies the differential equation dl, that is partial dl dy dashed, minus the total derivative with respect to x, the partial derivative of L with respect to y dashed equal to 0. And this equation we called the Euler-Lagrange equation. Sometimes we call it the Euler equation. And in the inverse problem, in variational calculus, in the inverse problem, we are given a differential equation and we're asking the question whether its solution satisfies or optimizes some integral. So given a differential equation, let's suppose the differential equation is of second order. So you'll have something like y double dash plus y equal to 0. So suppose we know the differential equation, suppose we know the solution of the differential equation. Does the solution of such a differential equation optimize an integral? So does its solution, and the solution obviously will be y equal to some function of x, does its solution satisfy, or I should say optimizes, does solution optimize some variational problem, optimize an integral, and the integral would be of course of this type. Stated in an alternative way, alternatively, right, can we write the differential equation? Can we find a function? Now this is the reverse problem. Can we find a function, say L of x, y, y dashed? Let me write it a bit better. Can we find such a function such that the differential equation I mentioned, the given differential equation, which recall was e of x, y, y dashed, y double dashed equal to 0. Can you find such a function such as given differential equation can be written in Euler-Lagrange form, can be written in Euler form or Euler-Lagrange form. And what is the Euler form? The Euler form is dl dy minus total derivative of the partial derivative of L with respect to y dashed equal to 0. And I mentioned that we had some examples of this type. Okay, if I give you the example y double dashed equal to 0, then if L equals a half y dash squared, the Euler-Lagrange form dl dy, you can check this, it's all in your previous notes. You put that equal to 0, you will get the given differential equation y double dashed equal to 0. An example that I may not have given you, if we're given the simple harmonic oscillator equation, if y double dash plus y equals 0, then it can be shown, and if L equals a half y dash squared minus a half y squared, let's do the various derivatives. The partial derivative of L with respect to y, and this is partial derivative, x and y dash are constants, so if you differentiate L with respect to y, you get minus y. Check that very easily. The derivative partially of L with respect to y dashed is equal to, you differentiate a half y dash squared, you get y dashed. And we need this to be differentiated with respect to x totally. So the total derivative of the partial derivative of L with respect to y dash, and this is now total derivative. If you differentiate this function y dashed with respect to x totally, you get y double dashed. And now put these terms into the Euler form, and here's, for example, an Euler form from the previous example. So we get, therefore, the Euler form gives, right, minus y double dashed. This minus comes from the partial derivative, and this minus comes from the Euler form, and you may recall that there's the minus sign in the Euler form. And that will equal 0. Sorry, let me change the color back to black. So this equals 0, and that implies that y double dashed plus y equals 0. And this is equivalent to the differential equation given above. So that we now say that the function L is a Lagrangian of the given differential equation y double dash plus y equal to 0. So this differential equation, does its solution would satisfy or optimize an integral of some type, where the Lagrangian, the L, would be this L. How did I find that L? Well, for now, let's just say it was a guess. There's a formal procedure for constructing these functions L if they exist. You may recall I mentioned that two problems prevail in the inverse problem in the variational calculus. One is, given a differential equation is it variational? In other words, does a Lagrangian exist? And secondly, if the Lagrangian exists, is it unique? If you go back to the previous notes, you'll find that, for example, y double dashed equal to 0, we showed had two very different Lagrangians. I will mention one type of example in which we construct the Lagrangian in some formal way. And here's the general formal way for these kind of examples. So consider a differential equation of the following type: a second order ordinary differential equation of the type y double dashed, say, plus some function of x p times y dashed plus some function of x times y equal to 0. So this is really a linear differential equation. What we do in an example like this is we multiply by what we call a variational factor. It's a standard thing to do to construct Lagrangians. So you multiply by a factor, and this will remind you of integration factors from first year. So multiply by a factor of the following type: e to the integral of p of x with respect to x. And once we multiply this differential equation by a factor of that type, we can sort out the inverse variational problem. So we're going to do an example of this type, a sub-example. So suppose we have a differential equation of this type, say y double dashed plus k times y dashed plus a constant, where k is a constant, omega squared is a constant, times y equal to 0. So you will note that in this case, in the notation of what we had above, the function p of x is a constant k, and the function q of x is a constant w squared, or omega squared. So here then we multiply by the variational factor, multiply by e to the integral of k with respect to x. K is a constant, so this is e to the, very simply, k goes out, dx. Well, you integrate dx with respect to x, you just get x. i.e., once we do that, the differential equation after multiplication by this factor becomes, we get that this is then e to the kx y double dashed plus k times e to the kx times y dashed plus omega squared e to the kx times y equals 0. If you look at the first two terms closely, that is the total derivative with respect to x of the following product. So it's e to the kx times y dashed. Check it. If you apply the product rule on e to the kx y dashed, you get the previous two terms. The third term, which is this one, can be written as a partial derivative. And remember, when you differentiate partially with respect to y, x and y dashed are constants. So if you differentiate this, you get omega squared e to the kx, and you're integrating y, so you get y squared over 2 equals 0. So that is the only function of y. You differentiate that, you get back your y. The omega squared and e to the kx are constants. Right, so we're almost there. We want the Euler-Lagrange form coming out of this. Leave this dx where it was, and if you take this bracket, you can write it as the derivative partially with respect to y dashed. So this is the partial derivative with respect to y dashed of e to the kx y dash squared over 2. So you differentiate y dash squared over 2 with respect to y dashed, you get y dashed. Plus, you get back that term, let's leave that as it is, equal to 0. Right, what do we have now? It's almost the Euler-Lagrange form. Let's write it in that form. If I write the first term, or rather the second term first, this is the partial derivative with respect to y of a half omega squared e to the kx times y squared. And then I'm going to take this term and write it in there, but I'm going to introduce a minus sign because the Euler-Lagrange form has a minus sign. This is the total derivative with respect to x. Partial derivative with respect to y dashed. I need to introduce a minus sign, so that is minus a half e to the kx and then y dash squared equal to 0. Check the derivatives. The minus times the minus times the minus gives me the positive I had in the previous step, and otherwise everything else is the same. Now this term here is independent of y dashed. That term there is independent of y. So as far as this term is concerned, I can introduce or add any term involving y dashed, and its derivative with respect to y will be 0, so it's a constant. And in this case, I can add any term involving y, and I will not change anything, because its derivative with respect to y dashed will be 0. So, watch this. I'm going to take the first term, that term, and I'm going to add in a term, a constant, but a specific looking constant. This is a half omega squared e to the kx y squared. I haven't changed anything, but I'm going to add this constant, minus a half e to the kx y dash squared. If I differentiate this term with respect to y, I get 0. So I haven't introduced any significant term. Then this is, the total derivative with respect to x, the partial derivative with respect to y dashed. I'm going to include the term I had in there from the previous step, but I'm going to add a constant. The constant will involve an x and a y. So this is a half omega squared e to the kx times y squared. So because of that squeezing, I'm going to write in the y squared now. So this is y squared equal to 0. Okay. So now look at this last form. You notice that what I have there is the same as what I have here, and I'm going to call that L. So I'll say O, I get d by dy of L minus total derivative with respect to x, partial derivative with respect to y dashed of L is equal to 0. If I define my L to be the thing I circled, which is a half omega squared e to the kx y squared minus a half e to the kx y dashed squared. So this then is the Lagrangian for the differential equation we were given earlier on. Now these Lagrangians exist, of course, even for systems of equations, but I will speak about the systems equations in perhaps the next lecture. We'll continue with an example, then I'll get into the very nitty-gritty of the relationship between Lagrangians of differential equations and what I'm going to call conservation laws. And this is going to be the central part of this course.